So one very commonly used electrophysiology technique is the EEG, or the electroencephalogram. And EEG allows for a recording of what we call aggregate brain activity. So this is like, many, many, many neurons that are firing sort of simultaneously, because you're going to be recording the electrical activity of these large, large groups of neurons, from electrodes that are placed upon the scalp. So this is actually considered to be a non-invasive technique. There's no implantation, of a deep brain stimulator, for example. There's no surgery involved. There's literally just, sort of the scratching of the scalp, with a kind of a grit that's added there to improve, to reduce the resistance, to allow for, these very small signals, aggregate signals of many, many neurons sort of firing together simultaneously to reach the surface and be detected by recording electrodes that are placed here on the scalp. And these neurons that you're actually recording, first of all, there's many, many of them firing at once. And also it's a very selective, set of them, because they have to be oriented in a particular way, for their, for this current to be detected, to reach the scalp too. And it tends to be, the areas of the brain that are closer to the actual, skull, right, to the scalp. So it's a very selective recording that we're actually getting. We're not getting all, the neurons that are firing in the brain. However, it provides important information about the state of our brain, which is why it's used clinically. For example, your level of alertness. For example, if you're very engaged and you're, let's say, visually engaged and like looking around, and you recorded from, electrodes that are placed over the occipital lobe, which is, the visual cortex, you would see, rather rapid, what's called beta wave activity and very low amplitude activity, because this represents many different sort of subpopulations of neurons in the visual cortex, basically processing different aspects of, the visual input through your eyes. So you're going to get that very rapid, low amplitude activity. But yet, if you close your eyes and you're relaxed, you get this thing called the alpha rhythm, right, which is much higher amplitude typically, because more neurons are firing together. They're entrained, to this sort of, alpha rhythm, which is not as fast as the beta, and many more of them are doing stuff, together, which is less informative. And in fact, when you start to get into sleep states, right, you start to see these great big, slower but higher amplitude waveforms, delta and theta waves. And, these represent many, many more neurons firing together, which is actually less informative. There's less information processing going on. So EEG is definitely able to tell us about, our state of alertness and arousal, the various stages of sleep that have been identified. It's interesting when you go into REM sleep, for example, which if you wake somebody when their eyes are rapidly moving back and forth, they tend to, be in the midst of some kind of dream state, right? The waveforms that you record in EEG are actually beta and low amplitude, more indicative, of somebody who is actually still awake. However, their eyes are definitely doing something very specific, and they're clearly asleep. The activity is being driven more internally than by, external sources. Drugs can certainly affect brain state. The caffeine that I've got right here has been known to, help to alert, your brain. So you can measure, those changes, directly using techniques like EEG. The other nice thing about EEG is that it's a relatively inexpensive technique compared to a lot of other imaging techniques like, PET and fMRI, for example. And also it's got very, very good, what we refer to as temporal resolution, time resolution, because it's giving you actual neuronal activity. It is aggregate and it's selective, but actual neuronal electrical activity, millisecond to millisecond. So it's got very, very good temporal resolution.